The central limit theorem is, as I said in a previous lecture, this is the basis for most of what we're going to do in the rest of the course. And so this is an extremely important idea, and it allows us to do what we do. And there's going to be a few phrases that I say quite often in this chapter or in this section, and I want you to make sure that you pay attention to them. Any distribution of sample means approaches normal as the sample size increases. We kind of said that in the last section. But again, this is the foundation for estimating population parameters and hypothesis testing, which we're going to get into in the next unit. When we have any random variable, we're going to call it x, and we know it has a distribution with a mean of mu and a standard deviation of sigma. That shouldn't surprise you. We've been talking about that for quite a while now. We need to have a simple random sample of a certain size, and if we look at the sample means of any statistic that we're interested in, when we look at the distribution of sample means for a parameter, it will approach normal as the size of your sample gets bigger. The standard deviation of that mean of the sample statistic is our population standard deviation divided by the square root of n. So what happens, the standard deviation when you're looking at a sampling mean is smaller than the standard deviation for individual scores. In practicality, we want the number in our samples to be more than 30. And then the distribution of our sampling means will be reasonably normal no matter what the shape that we started with. And if the original is normal, any number in the sample will give us a normal distribution. So here's the deal. When we talk about the mean of the sampling means, we use a mu sub x bar, because what that means is we found the mean of our samples. We put a whole bunch of those together and found the mean of the means, and it is going to tell us the mean of the population. The standard deviation of the sampling mean is the population standard deviation divided by the square root of the number in the sample, and that's because of this very, very, very important. But the average data is less variable than individual data. And that's really, really important. So no matter the shape of the population distribution, the sampling distribution approaches normal as the number in our samples get bigger. So here we go. We've got some dot plots here, and you can see with this first example, our population is normal. And when n is 1, that's just the individual data. Now, if we take many, many samples of size 10 from that same population, look at what happens. Okay, we get a normal distribution. Notice that its spread is less than when the sample size is 1. If we put our sample size as 50 and we look at many, many samples, again, you see that we get a normal distribution, and notice its spread is much less than when it's an individual. That's because our standard deviation of the sampling distribution is divided by the square root of n, and that's because our average data is less than the individual data. So average data is less variable than individual data. Now let's look at a uniform distribution. And so a uniform distribution, remember, is a rectangular distribution. So it would be similar to if we were going to toss a single die. And what would the number of pips on the face comes up, and we would expect 1 through 6 to happen at the same proportion, 1/6 of the time. If we take our sample size to 10 and take many samples of size 10 from our population, notice what happens. It gets closer to normal. Notice what happens. Our spread becomes less. When we up our sample size to 50, notice what happens. It's even closer to normal, and our spread is even less than, because average data is less variable than individual data. And we can even have a U-shaped distribution, or maybe you'd think of it as anti-normal distribution. And when our sample size is 10, you can see that it becomes closer to normal. When we up that to 50, it becomes closer to normal. Notice that the spread is much smaller when our sample size is 50, because, and I hope you are thinking it before I say it, average data is less variable than individual data. So as the sample size increases, the sampling distribution of sample means or sample proportions or approaches normal. Now remember, the sample variance will be a little bit skewed, but for sample means and sample proportions, this is the deal. And why is that? Because average data is less variable than individual data. So we have an example here, and this is an elevator example. It's a little different than the elevator example in your textbook, but it works. Okay, so on the little plaque, when you get inside, it says maximum capacity of 16 passengers, total weight of 2,500 pounds. Assuming the worst case scenario in which all the passengers are male, what are the chances that the elevator is overloaded? So we need to come up with a distribution, and we're going to assume that male weights follow normal distribution with a mean of 182.9 and a standard deviation of 40.8. Find the probability that one randomly selected male has a weight of greater than 156.25. Okay, let's back up just half a step. If we take our 2,500 pound weight limit divided by 16, we get 156.25 pounds. Okay? And then B, we're going to look at what happens with a sample of 16 men. What's the probability that the sample of 16 men will have the mean weight of greater than 156.25 pounds? So when we find the probability of 1, that's going to be very similar to what we did back in 6.2. So we're going to find the z-score, and we're going to look at that. We're going to standardize a score, and we get a negative 0.65. Let me pull in StatCrunch. So let's pull in StatCrunch, and remember that our z-score was a negative 0.65. Stat calculators, normal. I want, what is the probability that our score will be greater than, this should be a negative 0.65, and I get 74% of the distribution will be above that. So the probability of getting one man who weighs more than 156.25 pounds is about 74% of the time. And we had our standard deviation of 40.8, and we used that when we found our z-score. Now let's find the probability that a sample mean of 16 males have a mean weight greater than 156.25. So what we're going to do is we need to change our standard deviation, because now our sample size is 16. So we're going to take our population standard deviation, divide it by the square root of 15. So our new standard deviation is 10.2. It's been divided by 4. And so now our z-score is a negative 2.61. Notice how our distribution now is tall and skinny. Here it was short and fat when we were talking about one individual. So what we're going to do is let's look at this, and let's go back and let's take this to StatCrunch. And this time I want to use the standard score of a negative 2.61. And when I compute the probability of getting a mean of more than 2.61, a negative 2.61, is 99.5% of the time. There is a 99.55% probability that a sample of 16 males will have a mean weight of 156.25 or more. So in other words, there's a very good chance that the safe weight capacity of 2,500 pounds will be exceeded. And again, here is comparison of those two distributions. So the short fat one is for a single individual, but the tall skinny one is for a sample size of 16. So when we take the sampling distribution, what we're doing when we're skinnying up this distribution, we are honing in on the correct score. Our chances of being wrong are less because our distribution is not as wide as it is with one individual. So we've talked about the central limit theorem, we've talked about the practical rules, and we've talked about the effects of sample size. Let's do number 16 on page 274. Okay, we're talking about Coke cans. And Coke cans are filled so that the actual amounts are normally distributed with a mean of 12 ounces and a standard deviation of 0.11 ounce. Okay, find the probability that one Coke can, and I'm going to just put a 1 there, one Coke can has at least, so that means it could be more than 12.19 ounces. So this is part A. So okay, so I have a raw score, I need to standardize it. So my z-score will be my score minus the mean divided by the standard deviation. And when I do that, I get 1.73. So now I can go to StatCrunch, and when I put this in, okay, so I want to do, look at this, and I have found that my z-score is 1.73. So stat calculators, normal, and I want to see at least, so that's greater than, and my z-score was, and I'm going to compute, and that's 0.0418. So this probability is going to be 0.0418, or about 4% of the time one Coke can will be filled with at least 12.19 ounces. Okay, let's look at part B. Let's do 36 cans. And so now the number in our sample is 36. And they tell us that the mean of this sample is 12.19. So let's find the probability that the mean of 36 cans is going to be at least greater than or equal to 12.19 ounces. Well, we're going to find our z-score. And again, it's going to be 12.19 minus 12 comes out to be 0.19, but our standard deviation is going to be a little bit different. It's going to be 0.11 divided by the square root of 36. So when we do that math, we get a z-score of 10.36. That's a really, really huge z-score. Let's go back to StatCrunch and let's put that in. So this time our value is going to be 10.36 0.36. And we get a probability of 0. It isn't going to happen. So, meaning, now let's put meaning with that. I want to go back to that. We're looking for the probability way up here in this upper tail. You can't see what I'm doing, but way up in the upper tail. In other words, it says the area beyond where we're looking, there is none. So every can will be greater than or equal to 12.19. That probability is 0. That means every can has more than 12 ounces. And that would be every, well, in a group of 16, the probability that their mean will be more than 12.19 is 0, meaning that their mean is going to be above that, so we can assume that every can has more than 12 ounces. I hope that helps how you set it up. Good luck.